uh, ax plus by equal to c, where we know that the solution for linear differential equation is possible only if the GCD of a and b divides c. So linear, okay, LD, I will simply write. Ax plus by equal to c, where we know that the solution for linear differential equation is possible only if, okay, let me just type that. Ax plus by equal to c. This is what we want to solve. Am I audible? Okay. Ax plus by is equal to c. And if you want to solve, okay, we will take some a equal to some number. What was the number that previously we have taken? 1878. Large number itself we will take. B equal to 174. Okay, some space is appearing here. So 174 is here. And C, suppose that, and what is the GCD of these things we found? GCD we found to be, we didn't find the GCD, right?
Six.
So,
Yes, sir.
okay, we will find GCD insert. See, here the insert cell above means that if you want to perform some computation on the top of the existing cell, you may just click here and click on insert cell above or insert cell below so that you can get some extra space for computation here. I'm just using that extra space. GCD of AB, and that is equal to 6. Okay, so for this this LD, linear differential equation to be solvable, can somebody say that what possible value of c we can take? Some suggestion. GCD is 6. Some suggestion about c. This is a question to students, and
Multiple
anyway
of six.
it has to be a multiple of 6. Good, correct.
Six.
So this has to be a multiple of 6, and probably we can take it to be equal to say 18, right? There is no problem in taking 18 here, because of course we can take it to be equal to 6, but I'm choosing something different. So take it to be 18. Now, so the method to solve this question is, the method to solve this linear differential equation lies in expressing the GCD as a linear combination of A and B. That is the very first thing that we have to do. So, if we are able to express GCD, suppose that we are able to express D equal to AX naught plus B Y naught, and suppose that if C is a multiple of D, then C is equal to MD. Then solution, we know that it would be equal to, if we have found X naught, then M X naught and M Y naught will be the solution. Agree to that? So if we have D, if we are able to find x naught, y naught such that GCD is equal to ax naught plus by naught, and suppose that for solution to x, C must be a multiple of D. So suppose that C is equal to MD. So x naught and y naught gives D. So to get M into D, we need to multiply the solution also with M. Therefore, solution will be mx naught and m y naught. So of course, we can then find the general solution. I'm talking only about the particular solution. So to find a particular solution, we need to find a particular solution for D is equal to ax naught plus by naught. So the first thing is to compute the GCD D, that we have already done, but anyway, we will do it once again. GCD of A and B is equal to D. So that is computed. Now we need to find, the crucial step is to find x naught and y naught. In the notebook, if we try, we use several methods like for finding. See, this identity has some name. Can somebody recall the name of this identity? Can somebody recall the name of this identity? D is equal to x naught plus by naught, where D is the GCD. I don't know whether that name is appearing in that textbook, but this identity is known as, or D can be expressed as a linear combination of A and B. That statement is known as Besso's lemma or Besso's theorem. Besso is, I think he's a French mathematician, and the identity is known after his name. So the crucial step is to express GCD as a linear combination. But fortunately, there is a built-in function available in stage math for finding the x naught and y naught, and they are known as Bezos identity coefficients. And the command for finding the Bezos identity coefficients, I'm calling it as BIC. I'm just giving the name BIC. It is not necessary to give name BIC. Something else also we can put. So the command for finding Bezos identity coefficients is XGCD of A and B. So this simply means that give the coefficients x naught and y naught, so that D is equal to ax naught plus b y naught. Okay, let us see what are these coefficients. So I'm just printing that. So the command is xgcd for finding the Bezos identity coefficients. Command is xgcd. So if I press shift enter, the answer is this. So what are the numbers I have taken? 1878 and 174. And what was the GCD? GCD is 6. So it says that 6 is equal to minus 5 into A plus 54 into B. Okay, let us see if it's correct or not. Print minus 5 into what is the value of A? Value of A is 1878 plus 54 into B. To see the answer? Okay, so it says that that is equal to minus 5 into A plus 54 into B. So it says that that is equal to 6. Therefore, the Bezos identity coefficients are minus 5 and 54. So x naught is minus 5 and y naught is 54. So x naught equal to, we need not write minus 5 because this is the, see, this whatever is written in ordinary bracket in Sage is known as a tuple. So this is a 3 tuple. So to get the first value from this tuple, we may write BIC 0, but we need x naught. Therefore, it is BIC 1. This is second value. The number counting in Sage starts with 0. So this is the 0th element in BIC. This is the first element in BIC. This is the second element in BIC. So x naught is nothing but BIC 1 and y naught is nothing but it is equal to BIC square bracket. Remember that square bracket BIC 2. So two numbers are here. And now what is the solution? Solution, we know that it is equal to, if C is equal to MD, the solution for our original equation is mx naught plus mx naught and my naught. So x naught is here, x1 is equal to d into d is what? D, not D, sorry. We want C is equal to MD, so mx naught, but M is nothing but C by D. C, okay, we will even write that. That's better. M is equal to C by D. So x1 is equal to m into x naught and y1 equal to m into y naught. So we are going to print finally a solution is, so what are the values that we are getting? A solution is x1 y1. So the final output is, a solution is minus 15, 162. So for the linear definite equation, 1878 into x plus 174 into y equal to 18. A solution is x1, y1, and the value is minus 15 into 162. Now, how to find the general solution for this? We know that general solution is, how to find the general solution? General solution is nothing but that is equal to, how to find that? X naught minus x naught plus m into, general solution is x naught, not x naught here, here it is x1, x1 plus b by d into some q or t, and y1 minus a by d into same t. This is the general solution. But not that, to display the general solution, we need to display something like t. But t is a variable. T is not a concrete number. So we define t to be a variable or a symbol. So var stands for defining a variable or symbol. So var in quotes we are writing t. So we are going to print the general solution. Print general solution is, we are going to make use of all these things. X1 is already known to us. X1 plus b by d, or maybe we can put a bracket here, b by d into t, and y1 minus a by d into t, and closing the bracket. So finally the solution is minus 15. See, in Sage, usually it tries to arrange the polynomial in such a way that the largest power comes first. So this is actually a polynomial. 29t minus 15. Usually in our notebook, we write it as minus 15 plus 29t and 162 plus minus 313t. So this is the general solution for the linear definite equation 1878x plus 174y equal to c. So we completed the solution for a linear definite equation, and we did not actually check if it divides or not because we initially took C in such a way that D divides C. But of course, we need to perform a check here. We need to perform a check in the sense that we need to check if GCD of AB, that is D, divides C or not. After that only we should actually proceed. So if D divides C, this is how we find a this is how we find the general solution for this linear definite equation. So if there is any question, you may ask now, please.
Participants, if you are having any doubt, unmute yourself and ask your doubts.
I think there is nothing. So if there is nothing, we will proceed. Okay. So the linear definite equation is now solved. What is now next? Okay, now to find the GCD of, we have seen that we can find the GCD of two numbers by just inserting the two numbers inside a simple bracket. But how to find the GCD of three numbers? For example, 12, 15, 18. So if we use, since there is only one line, we can avoid using print. See, we are seeing an error here. GCD of 12, 15, 18. If we put three numbers in this bracket, we are seeing an error here saying that GCD takes 1 to 2 positional arguments, but 3 were given. So it means that if we can give one number or two numbers, but we have given three numbers, that is not allowed. So to find the GCD of three numbers, what we have to do is we have to input the three numbers as a list in this way. So enclose them in a square bracket and feed them to the GCD function. So we will get GCD equal to 3. Similarly for LCM also we can do exactly the same thing. So if you want to find the LCM of more than two number, you have to enclose them in a square bracket. Enclose the three numbers in a, and this will work for more than 3 also, 24. So if you have more than two numbers, then you need to enclose them in a bracket like this. This is how we find the GCD of more numbers. Now, what is left now? So the next thing. Okay, now we will go to prime related functions. So we are proceeding to prime related functions. So the first command that we want to check is how to check if a number is prime or not. Suppose a is equal to 35. So to check if it's a prime or not, the question is quite simple. We need to just ask, is prime a? So if you are asking this question, Sage will say that false. That means that it is not a prime. So is prime will let us check if a given number is prime or not. Now on the other hand, if we try 17 So a equal to 17, print is prime a. Sage tells that it is true. That means that is a prime. So is prime is a function available in Sage which will check if a given number is prime or not. Now, how will you find all ranges in one given range? Or how will you find first 100 primes? So suppose that we want to find first 100 primes. The technique is print the list of 100 primes. That's it. So to find first 100 primes, we need to just, sorry, this is not first 100 primes, this is actually primes up to 100, not first 100. So to find primes up to 100, we need to use the command primes, and in bracket we need to give the number up to which we want to find the prime. So let us see if this is inclusive or not, inclusive of the last number or not. If we give 97, okay, 97 is also included. Therefore, primes function will give all the primes up to a given number and including that number. But there is another command also that will list all the primes in the given range. Instead of starting from here, we are starting from 1. But instead of starting from 1, we can just use one more command, which is print prime range from 1 to 100. If you use this, the same output, what about giving 97 here? But here the difference is that if you are listing, oh, this is 97 is not given here. Okay, even here 97 is not included. Sorry, that is actually a mistake. So when we are giving primes 97, 97 itself is not included, and just below that will be included. Here instead of that, if you give prime range 197, it will find all primes from 1 to 97. So if you give 10 to 97 instead, so it will list all the primes in the range 10 to 98. 97 is not included. That is actually a common property in the case of all Python related software, that whenever we have a list, whenever we are trying to find out numbers in a range, the last number will be excluded. So you have to be careful about that. This is how we find primes in a given range. Now, if you want to find all primes, all first 100 primes, the command is slightly different. So to find all primes, print primes first n. So first n primes. Suppose that we are giving 100. So here we have 100 primes. So primes first n means that give the first n primes, where n is this 100. So now we have seen three commands. Is prime, that tells us if a given number is a prime or not. Second, primes, but here we have the list. If we remove this list, what happens, we'll see. Suppose that we will just remove this. So it will not give. Sometimes Python creates, Sage creates something in another object. So to see the list, you need to use the list command also together with that primes command. Primes, that is another command. Prime range. So this is used for finding primes in a given range. Primes first n. So this will give all the first n primes. So these are the commands that we have seen related to primes. Now, if you want to find the number of primes up to 100, the function is known as prime pi. So how many primes are there up to 100? There are 25 primes. The command is prime pi. How many primes up to 100? So if you see 97, is it included? Yes, here it is included. So you have to be really careful while designing your program. In some programs, that number itself is included, and some programs that is not included. This is basically because a Sage is not written by one person. Sage software is it's created as a contribution of many. So um, we cannot expect each and every function to behave exactly in the same way. So some functions will include the last number, some functions will not include the last number. Now, to get the nth prime, there is another function, there is another command, but before that, there is something known as P equal to primes. This is a way to create the set of this. Now P is now the set of all primes. So if we print P, it will say now P is the set of all prime numbers. So if you want to ask, we know that by a famous result of Euler that the cardinality of primes is infinite. So we'll just ask for the cardinality and we get that the cardinality of primes is infinite. So P dot cardinality. So if you have a set, we can use the command dot cardinality to find the cardinality of that set. So to find a prime number which is at the 10th position, suppose that we want to find the 10th prime, the command is P unrank. So this will give the 10th prime, that is 31. Okay, see here 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is because the first prime is actually the zeroth prime. First prime is actually the zeroth prime because counting is always, this is n. First prime is there, first counting starts from 0. Therefore, if we give n equal to 10, we will be actually getting the 11th prime, not the 10th prime. Okay, this is how we find out all the primes. All the primes. So these are the basic commands about primes. We can find nth prime. We can find primes in a range. We can find. We can check if a given number is a prime or not. Now, next question is about finding divisors. So finding divisors in Sage is very easy. I just use the divisors function. Print divisors of A. That's it. We get it as a list. A list is a numbers enclosed in a square bracket separated by comma. So that is what simply a list is. So we get the divisors of A as this. Command is divisors. Now, if you want prime divisors, the command is prime underscore divisors, and you will get it to be equal to 2, 3, 3, 1, 3. Therefore, there are 3 prime divisors. So how many divisors are there? To find, we can use the command to find how many divisors are there, length of divisors of A. Yeah, we get that 8 divisors are there. We can see it here 1, 2, 3, 4, 5, 6, 7, 8. There are 8 divisors of this uh, A equal to 1878. And how many prime divisors are here? So that also we can use the same length command. Length means length of the list. So we get it as 3. So this is how we find divisors and prime divisors of A. Now, if you want to factorize, we have the factor command. So factor command will give that, okay, there is no multiplicity. Therefore, factor command will give that A is equal to, A is what? A is equal to 1878, and 1878 is nothing but 2 into 3 into 313. Now, factor 100. That gives 2 square into 5 square. That means 2 appear. This is the prime factorization or canonical decomposition, whatever. So factor command will give the prime factorization of a number giving the multiplicity. The multiplicity is 2 here. The multiplicity of 5 is 2 here. So 2 times 2 and 2 times 5. This is how we factor in SageMath. Now prime divisors we have seen, and okay, and I have already told you that the cardinality command can be used in any set. So how do we define a set? To define a set, we use this structure. 1, 2, 3. So see that, how did I define a set? I enclosed, I use the command set, not that this S is capital. After that, a simple bracket, then list of elements included and then enclosed in a bracket. So if I print a, so a is given as one set 1 2 3, but now the question is, can I define b equal to 1 2 5? Yes, we can define using this also. There are two ways of defining sets. One is using the set command, and the other one is using the directly this. Now, if you want to see what type of element this B is, there is a command known as type. What type of object, what type of element this B is? You may see that this is equal to set. But if we check the type of A. See, these two are giving actually, we are actually getting two different answers. Here we have constructed A using the set command, but here we constructed B using ordinary set bracket. If I'm typing print type of B, I get simply set. But if I get the type of A, I'm getting sage, set object, etc. So these two sets are actually slightly different. In the sense that if you are familiar with the Python language, this is actually a set created by the Python language, and this set is having more features than the set B has. So these two sets are slightly different, and whenever you are defining sets in Sage Math, it is better to use this notation, set with S capital, instead of using this ordinary this double curly brace brackets. To define sets, use this. And now if you try a dot cardinality, that is 3. What about b dot cardinality? That is not working because this b is created using some other command, and the cardinality extra like commands will not work on b, but a is created using the set command. Therefore, cardinality and many other set theoretic commands that is available in Sage will work on a. So whenever we have to define a set, define set in this way. Do not use the simple notation. Use this notation so that we will be having some extra features supported by Sage Math. Okay, now what is next? So now we will see how to convert among different number bases. So number bases. This is a standard problem in elementary number theory, that how to convert among number bases. So to convert a number into any other base other than decimal, we use the following symbol. So suppose that we want to convert a number 100 to base 2. This is structure that we use. So this is the command. So if you want to convert 100 to base 2, the command we have to use is 100.str and base 2. So if I print, let us see what happens. Result is 1100 100. So what about base 8? 144. What about base 16? This is equal to 64. So the command for converting a decimal integer to any base, we have to use that number dot str in the bracket, give the base. This is how we convert from any integer, any decimal integer to some other base. But now if you want to convert from any other base to decimal base, we need to tell that which base from which base we are converting. So the command for that is this. So 1111. Okay, instead of that, I will use this. So this we have to enclose in a quotes, a pair of quotes. So integer command needs to be used, and we need to specifically say that this string, this is actually a number in base 2. So if you convert it back, we get this to be equal to 100. See that we had converted. So these two are opposite commands, 100.str and integer in this. So we will once again see this. So integer, this is the command that we are using. In close bracket, we have to give the number to convert in quotes. And after that, we have to mention that this given expression is in which base. Okay, now 64, we'll see 64 and base 16, that is equal to 100. So these are the opposite commands for conversion from decimal base to a non-decimal base and from a non-decimal base to a decimal base. And I think that's only that is there are these are the only things about conversion among different numbers. Now we will see how to define the permutation, combination, etc. That is actually some other topic in this thing. So, okay, before that, we need. So, what is the next topic available in number theory as per the syllabus? What is the next one? Okay. The next topic available here is, I think, modular arithmetic. Okay, we will go into modular arithmetic. And to perform modular arithmetic, it is quite straight away, it's quite simple. Suppose that we want to perform the modular arithmetic, then we need to, so now we are going to use modular arithmetic. So whatever line we start with the hash symbol, that is treated as a command and that will not have any effect on the computations inside this cell. So suppose that I want to find what is going to be 5 or 15 mod 9. 15 mod 9. The command is modulus of, see, mod, this is equivalent to saying 15 mod 9 and turns out to be equal to 6. So A equal to, let me just type something like this. A is equal to this, B equal to, right, say 11 mod 9, print A, B. So it's printed as a 6 and 2. We print A plus B, and the answer is now 8. Is that correct? 15 plus 11, that is 26. 26 mod 9, that is equal to 8. So the answer is correct. Therefore, we have converted A and B into congruence numbers. Not They are not actual numbers. They are congruent numbers. They are in Z9. These are elements in Z9. So this is the command that we use for finding modulus or a remainder. This is actually the remainder. 15 divided by the 9, the remainder is 8. But if we write like this, whatever operation we perform after that will be automatically translated into the modular language. For example, suppose now that a to the power, so a is 6 modulo 9. So a to the power 2, print a to the power 2, a square. So according to our calculations, 6 square is going to be equal to 36, but Sage now understands that we are defining this A to be a congruence number, congruence class. Therefore, it gives the answer as 0. Is that correct? Oh, that is not correct. Why is it coming like that? A square. What is A square? That is correct. Because A square is 6 square. 6 square and that is 36. And 36 modulo 9 is going to be equal to 0. This is how we can perform modular arithmetic in Sage. If there is some question, you may please ask now. So we have started this modular arithmetic. Now we are going further. Please, if you need some clarification, please ask. Okay, there is nothing. I am proceeding. So So to check the integers in a range that are congruent to one particular number, we can follow the, okay, that is not actually necessary. Now, how to find if a number is invertible? Okay, next thing probably we will try to see is check if a given number is invertible modulo a congruence. If it is invertible modulo n. So we take a to be equal to 15 and m to be equal to say what number I should take, 7. So how do I check if these two, if a is invertible modulo 7? If GCD of, we know that a is going to be invertible modulo 7 if and only if GCD of a and m is 1. That means they are lately prime. So if GCD of 15 or a m equal to 1, then we will print a is invertible. Invertible, and we can of course print the inverse also. We can print the inverse also, but how do we print the inverse? We should probably take modulus of a with respect to m, and then we need to find the inverse in this way. Inverse is found as -1, and the inverse is, okay, how to check a number is invertible modulo n. So if a is equal to 15 and m is equal to 7, if the GCD of a and m is equal to 1, we will say that a is invertible. And in that case, we will find the inverse using the command modulus of am to the power -1. Let us see. So 15 is invertible and inverse is 1. Is that correct? Yes, that's correct, because 15 into 1, we will get it as equal to 15 itself. But 15 modulo 7 is going to be equal to just 1. Now let us modify it slightly. 10 and 8. Oh, but we haven't printed any. Yes, yes. Print A. A is not invertible. Okay. So the answer is 10 is not invertible because GCD of A and M is not equal to 1. See, this is quite useful for when we are trying to solve some linear congruence equations. So we know that linear congruent equation we can solve provided that the GCD of was two numbers is going to divide the other number. That is one case. And when the number is actually invertible, we can quickly find a solution. So this technique can be used for solving uh, congruence equations. Whenever we have to solve congruence equation, we can use this technique. Now we will see one problem where we are going to solve a congruence equation, and congruence equation is this. Suppose that we use the following three numbers. Solving linear congruence in one variable. Suppose that I'm choosing a to be equal to this, b to be equal to. So the question that we are trying to solve is ax congruent to b mod m. So here the equation is 12x congruent to 18 mod 15. So the first question is this solvable? Is this solvable? And what is the condition for ax congruent to b mod m to be solvable? That is the first question that we would like to see. So how do we check if this is solvable? Question number one. Can anybody answer? How do we check if this is solvable? Any answer? think you might have already gone through, students might have already gone through this thing in their elementary number theory class that AX, this is actually, this AX, this is congruent to, I cannot type the congruence here. Of course, I can type congruence if I use some LaTeX notation. But AX congruent to B modem is solvable. We know that this is possible if I relieve the GCD of A and then divides B. That is the first thing that we have to check. So if GCD, okay, we will take the GCD as D, GCD of A and B, and if D divides M, D divides them means M percentage D equal to 0. So that is how we write D divides M equal to 0. Then the congruence is solved. Then only the congruence is solvable, and otherwise this is not solvable. So M percentage D has to be equal to 0 first. So if this is solvable, how will you find the solutions? Of course, there are different ways for finding the solutions, but one way is to, of course, try with some trial and error. And since there is only M equal to 15, there are only how many numbers are there that we have to verify? So 0 to 14 numbers we have to verify. And once we get one solution, we know that we can find the other solutions by taking x naught plus what is it, x naught plus a by d into t. We know that. So it is enough to find one solution. But that one solution, how will you find? So to find one solution, we need to just take all the elements in all the elements from 0 to 15. So we are taking a list of numbers 0, 1, etc. 15. Not that this is quite valid sorry, 15 is not required, 14. This is valid in stage 0, comma, 1, comma, just 2 dots. Don't put 1 dot, don't put 3 dots. Exactly 2 dots, comma, 14. So Sage will interpret this as a list of numbers 0, 1, 2, 3, etc. to 14. Now we need to verify that which one will give actually an answer. So we will see, we will substitute this into AX congruent to B, and AX, we will substitute this into AX and see if it's becoming equal to B or not. Print if what we have to type, A star, in the place of X we have, we need to verify one by one. So for X in numbers, so see that I have used a command called for X in. You can see that these things are appearing in different color. For is appearing in it's appearing in bold as well as green. In is also bold as well as green. If is also bold as well as green. S star X. What should I type? Okay, modulus is required. Mod A star X M, that M equal to mod B to the modulus M. Then we say a colon, not semicolon, but colon, print X is a solution. So let us see what are the solutions here. Okay. So we are not getting any solution for this. But why is that? M percentage D equal to 0. What is the GCD of A and B here? GCD of A and B is nothing but this is equal to 3. And 3 divides 15. That is correct. But we are not getting it here. Why? 12, 18, GCD. Okay, we'll print GCD also. Print D. Oh, sorry. GCD, we are getting it to be 12 and 18 is 6, not 3. So we should modify it. 30. Okay. Even 30 it is 6. So 24. No, we need it to be a multiple of 3 alone. So 27. It's better. Okay, fine. So that is not correct. Okay. Now we get that congruence is solvable. Now we get 1 to be a solution. Why 1 is a solution? If we take A into 1, that is 12 into 1 12 into 1, but 27 modulo 15 is going to be equal to 12, therefore 1 is a solution. So 1 is a solution, 6 is a solution, and 11 is a solution. Therefore, the solutions are 1, 6, and 11. So we can solve a linear congruence equation in one variable like this. The things that we have to keep in our mind is m percentage d, the modulus percentage d has to be equal to 0. In that case, we should list all the numbers from 0 to m minus 1. Okay, here, instead of 14, we can say m minus 1. And if for x in this 0 to m minus 1, see if ax modulo m and b modulo m are the same. If they are the same, we say that x is a solution for this congruence equation. So this is how we solve linear congruence equations. Is there any question? You can of course interrupt me whenever, if you feel that there is some doubt, there is some clarification required. Please just interrupt me. So you don't have to keep quiet. You may just ask me if there is something you want to ask. Okay, I'm proceeding further if there is no question. Okay, the next problem that we would like to see is something known as I think in the syllabus we had what were the problems that we have, problems listed where one is finding a general solution for the linear definite equation. The other one is finding the what is that, Pollard's row factorization method, Pollard's p minus 1 factoring method, I think, right? So these were the two problems that is listed from the number theory portion as problems for performing practical computations. Therefore, we will try to see the Pollard's factorization p minus 1 factoring method now. And the Pollard's p minus 1 factorization basically depends on one. So how many of you are familiar with Pollard p minus 1 factoring method? How many of you are familiar with Pollard's p minus 1 factoring method? Is there anybody familiar with this method? I think that is actually given in that is given as for something to it's a part of the syllabus in number theory, I guess, right? Okay, so this congruence is okay. This part we have done already. Now the plots row factorization method, and okay, I will just copy paste what I have prepared. So this is what Pollard's p minus 1 factoring method is. So p minus 1 factoring method, we need a composite number or integer. Okay, we will choose an odd integer n equal to 1723. So it's an odd integer. P be a prime factor of n, but we don't know a prime factor of n. So Pollard's p minus 1 factoring method actually tries to find one factor, tries to find in fact one factor for this given integer, but we don't know any factor. As of now, we don't know any factor of this integer. So we are trying to find out at least one factor, and the number we are choosing is n equal to 1723. Now, the next step is to see the basic idea behind Pollard's factorization is there is something known as Fermat's little theorem is there. Fermat's little theorem says that if A and B are lately prime, so if A, P, if GCD is 1, then A to the power P minus 1 is equal to 1 mod p. This is what Fermat's later theorem says. So Pollard's p minus 1 factoring method depends upon this Fermat's later theorem. So we fix n first, and after that, the next step is we don't know if there is a prime factor. If there is, we don't have any idea about that. But anyway, we are going to choose a an integer k that is large enough. So large enough in the sense that is large enough compared to the speed. So then the technique is then 2 to the power p minus 1. Suppose that p minus 1 divides k factorial. So p minus 1 divides k factorial. Hello, am I audible? Hello? Hello? Am I audible?
Yes, sir.
Yes, sir.
Yeah, I lost the connection between. Sorry. Yeah. Okay, let me start sharing the screen once again. So is this visible? So is the
Yes,
screen?
sir.
Okay. So the basic idea is to just take a second. Let me just. Just one second. I'm trying to share something that is where this Pollard's factorization, this thing is explained. Okay. Are you able to see this window? Pollard's p minus 1 factoring method.
It is visible.
Yeah. Okay. So the Pollard's p minus 1 factoring. See, to do any problem, to do any program in stage math, you need to understand the basic idea behind that. So without that, it will be difficult. So one problem that we have to do in the stage math course is something related to Pollard's p minus 1 factoring method. So for using the Pollard's p minus 1 factoring method, we need to understand the basic concept behind that. So the basic concept is initially we need to choose an odd integer n. Why we are choosing an odd integer? Because we are using this Pollard's factorization to factorize a number. So if it's already even, we know that 2 is a factor. So there is, we can remove 2. So if it's again even, keep on removing 2's. So finding if 2 is a factor or not is it's very easy. There is no problem at all. So we are not at all interested in finding uh, 2 as a factor. Therefore, we will assume that whatever number we have to factorize is an odd integer. That is necessary to assume. Second thing is, and we need to know if it's composite or not. But of course, it's not always going to be true because we may not know if it's composite or not. We will assume that it is composite. And now suppose that p is a prime factor, and in such a way that the prime factors of p minus 1 are relatively small. For example, suppose that we consider we have the prime, we have already listed a few primes previously. If you are taking two primes, 100 and uh, so suppose that is 97 a prime, 97. I think 97 is a prime. So if you take 97 minus 1, 97, yes, 97 is actually a prime. We had seen that. If you take 97 minus 1, that is going to be equal to 96. Now, what are the factors of 96? How can we factorize 96? 96, of course, it's p minus 1. What are the factors? What are the prime factors of 96? 96 already has 30, 2 into 3. So 3 is a factor. So 32 means that it is 32 is having factors only 2. So 2 to the power 5. So 96 is 2 to the power 5 into 3. So 96, of course, is a big number comparatively, but the prime factors are very small. So we are, if p is a prime factor such that the factors of p minus 1 are relatively small, and now we consider a large k, a large enough positive integer. See, these things large enough, all these things are quite vague. Of course, when we are doing the problem, that will become more clear. So if we choose k to be a large integer such that p minus 1 divides k factorial. So, for example, if we take a 2, 3, see, for the case of 96, we have 97, we have 96, and 96 has factors. What are the factors of 96? 2 square is there, and then after 2 square, what are the other factors? 2 square, sorry, not 2 square, 2 raised to 5, then 3, the 2 and 5 are the only two factors. So, what is the k that we can choose so that uh, p minus 1 divides k factorial. What is p minus 1? P minus 1 is 96. 96 divides k factorial. How do we find k such that p minus 1 divides or 96 divides k factorial? Any idea? Any idea? We have p minus 1 is equal to 96. 96 is equal to 2 to the power 5 into 3. We need a k in such a way that p minus 1 divides k factorial. Any idea about that? Anybody can suggest some k? See, that k factorial means that we can take all integers up to k. For p minus 1 to divide k factorial, so k factorial must definitely contain 2 to the power 5 and k factorial must contain 3. Therefore, if you take any integer greater than or equal to 3 as k, definitely 3 will divide. So we need 2 raised to 5 also to divide k. So 2 raised to 5 simply means that we need 5 2's. So 5 even integers are more than enough. So how will you get 5 even integers? 2 itself is an even integer, 4 is there, 6 is there, 2, 4, 6. Now 8 is there, 10 is there. Therefore, if we choose 10 factorial, 10 factorial already contains 2 raised to 5. 10 factorial contains 3 also. Therefore, 96 divides 10 factorial. Is that clear? So 96 divides 10 factorial, and we didn't go for a very large k. We just see this is possible because we have p minus 1 having small prime factors. Therefore, we can take some k which is not very large, but at the same time p minus 1 divides k factorial. Okay, so p minus 1 divides k factorial. Now, what about 2 to the power p minus 1? Remember that the prime p is different from 2, of course. So it's because n is an odd integer, therefore any factor of n is going to be odd. 2 is different from p. So by Fermat's Little theorem, we know that a to the power p minus 1 is 1. Therefore, 2 to the power p minus 1 is 1. But now p minus 1 divides k factorial, therefore 2 to the power k factorial is also 1. So 2 to the power k factorial is 1 means that 2 to the power k factorial minus 1 is a multiple of p. So p to the power 2 k factorial minus 1 is a multiple of p. Now p divides n. Now p divides 2 to the power k factorial minus 1 also. So p divides both. So if p divides two numbers, then p divides the GCD. So p divides GCD of 2 to the power k factorial minus 1 and n. So the p is now included in this number, GCD of 2 to the power k factorial minus 1 into n. sorry, GCD of 2 to the power k factorial minus 1 comma n. So p is included in this as a factor. So to find p, it is enough to just analyze this GCD of 2 to the power k factorial minus 1 n. So this is the final aim we have. So we took, we keep on taking k's, and we keep on taking GCD of 2 to the power, GCD of 2 to the power k factorial minus 1 n. And if you are getting a prime factor for this 2 to the power k factorial minus 1 comma n, that prime factor is a factor of this n also. So if you get a prime factor, the factorization is over. This is what we are going to do in the Pollard's P minus 1 factoring method. The technique is quite simple, and let me show that technique now. So I will just present the Jupyter window. Okay, it is here. So n is chosen to be equal to 1723, and we are, see, definitely we know that we need to, so to find the prime factor of 1723, we need to go only up to square root of 1723, because we know that if at all there is a prime factor, we can definitely find a prime factor below this 1723. Therefore, we can fix an upper bound for this k. Okay, we can fix an upper bound for this k, and beyond that k we don't have to probably go for. So k we choose to be equal to floor of square root of n. Therefore we get k to be equal to 41. So now we are going to, okay, don't, not k, we will keep this as upper bound. So for this is the upper bound we are going to verify. For k in range from where to where we will try, we are going to keep on varying this k. K in range, we don't have to check to this u. We are going to perform the following computations. See that we need to take the GCD of, see here, we are taking the GCD of 2 to the power, what is it, GCD of, what we have to take, okay, let us take x to be equal to 2 to the power x equal to 2 to the power k factorial we have to take, but modulo n. So we will take x equal to modulo 2 modulo n, so that our computations will be easier. So x is 2 modulo n, therefore x is now 2, but it is modulo n. So now we have to take 2 to the power k factorial minus 1, GCD of 2 to the power, what is k factorial? We need to find the GCD of x and n, but x we are going to keep on varying. So initially, what is the value of x? The value of x is going to be equal to just 2. So d is equal to GCD of these two. D is this. We copy this. Now we will print k, x, and d. What is k? Our k is this. So if d is already greater than 1, suppose that GCD is already 1. So if GCD is not 1, we will keep on increasing the power of this x. If d is 1, we get a factor and we break. Otherwise, we will increment the power of x by a k. Okay, let us see what happens after that. So we are getting something like this. See here, let me just try to explain this. So here we have chosen this k to be equal to x to be equal to 2 modulo n. So here we have to keep on finding 2 to the power k factorial minus 1. That is what basically we have to find. So how will you find 2 to the power k factorial minus 1? So to find 2 to the power 3 factorial, it is enough to find 2 to the power 2 factorial and then take the power 3. So is that clear? So to find, so I'll just explain. Let me just explain once again. To find 2 to the power 4 factorial, we can find 2 to the power 3 factorial and then take the power to the whole power 4. Is that clear?
Yes, sir.
So see, once you find 2 to the power 1 factorial, how will you find 2 to the power 2 factorial? So already you have found 2 to the power 1 factorial. Then just take a square of that. Now, once you find 2 to the power 2 factorial, how will you find 2 to the power 3 factorial? So already you have taken 2 to the power 2 factorial. So take a cube of that. Now, how will you find 2 to the power 5 factorial if you have already found 2 to the power 4 factorial? Take 2 to the power 4 factorial and take a fifth power of that. That is what basically here also we are doing. See here, x is nothing but this is 2 to the power 1 factorial, right? X is just 2. 2 to the power 1 factorial modulo n. So x is just 2 now. Here, now we are considering x is a GCD of 2 to the power, see x is 2. 2 to the power 1 factorial minus 1 and n. Okay. X is nothing but 2 to the power 1 factorial because it is just 2 to the power 1 factorial. Now, in the first step, we are finding the GCD of 2 to the power 1 factorial minus 1 and n. Agree to that? So we are printing this value of k, we are printing the value of x, we are printing the value of d. Now,
Yes,
if,
sir.
if d is greater than 1, we found a common factor among x minus 1 and then we stop because we found a factor for n. We found a factor for n which is greater than 1. So if this is not the case, then okay, this is stop. If this is not the case, then we again take the second power. Now what is 2? Now what is x? This is 2. 2 to the power 1 factorial. What is the value of k? The first value of k is 2. So 2 to the power 1 factorial to the power 2. So that will become 2 to the power 2 factorial. So 2 to the power 2 factorial. Now we again find 2 to the power 2 factorial minus 1 n. Again check if d is greater than 1. If d is not greater than 1, now x is 2 to the power 2 factorial. Take cube, therefore it will become 2 to the power 3 factorial. Keep on doing like this until you get the GCD to be greater than 1. And if we execute, we get here 1, 1, 1, 1. Okay, we are not getting anywhere 1. So what are the numbers that we have taken? N is equal to, is this itself is probably a prime. I don't know. Okay, maybe 1, 7, 2, 7. Okay, see, I'm choosing 1727 as the number. So we get a factor as 11. So this is how we proceed in the Pollard's P minus 1 factorization, and the factorization consists of only 3-4 lines. Yeah. Please just go through this and ask me if there is some doubt. Go through this algorithm and ask me if there is something remaining to ask. So is there any question about either this algorithm or about the program?
No, sir. Clear.
Okay, now probably we have two more things to probably finish in number theory. We have seen Pollard's row factorization, sorry, not row factorization, it is P minus 1 factorization. And the next method is probably that We will try to, okay, the permutation and combination that we haven't explained. Modular arithmetic, we have already seen how to do that. Now, the next thing is how to perform uh, what you call this permutation, finding permutations and combinations, or basically combinatorics. That's it. So everything else we have finished. Now we will go to permutation combination and finding NCR, for example. Finding NCR, that is quite easy, and we need to just print the binomial coefficient of 5, 2. 5, 2 means that binomial coefficient of 5C2. 5C2. This is how we find the binomial coefficient of 5C2. If you print the binom, sorry, binom. So binom is not defined. Just 1 second, let me correct the command. This is binomial, not even binom, it is binomial. So, yeah. So 5C2 is nothing but it's equal to 10. So any number we can find like this. 10, 10. We get it as equal to 1. Now to find the permutations also, we have to more or less the same command we have to use. Of course, we can check if this fact is the 5, 2 is going to be equal to, according to our previous knowledge, we know that binomial coefficient of 10, 2. What is the definition for binomial coefficient? You know that this is equal to, so NCR is equal to n factorial 10 by factorial n minus r 10 minus 2 into factorial 2. Let us see if it's correct. Yes, says that this is true. Means that whatever the expression we have written, that is correct. That is binomial 10, 2 is equal to NCR is equal to n factorial by n minus r factorial into r factorial. So for finding the permutations also we have to use the same style command, but the only difference is that if we ask for the permutations of 5 to say, so 5 PR we want to find permutations. 5, 2, let us see what is the output. Permutations of 5, 2. It is not giving the permutations of the number of permutations of two objects, number of possibilities of two objects taken 5 at a time with position mattering. So this actually gives the set. To find the number of permutations, we need to take permutations of the length of this list. This extra command is required. So we get this to be equal to 20. Is this correct? So 5, 2. So that means that 5 factorial by 2 factorial, right? So 5 factorial by 2, 5, 4, 3. So this is wrong or what? 5, 2. What is the definition of 5 PR? Is that 20? 5 objects, 2 objects taken. Okay, let us list. Let us see the list of all these permutations and see. List. So 1, 2, 1, 3, 1, 4, 1, 5, 2, 1, 2, 3, 2, 4, 2, 5, 3, 1, 3, 2. Okay, all these things are listed here. So 5, 4. Okay, what is missing here? Permutations 5, 2, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 1, 2, 3, 2, 4, etc. So 5, 2, 3, 5, 4, 1, 5, 2, but 5, 1 is already included. So 5, 2. So what is the problem here? List of 5, 1, 1, 5. So how many numbers are listed? 20. Okay. So permutations. NPR, according to what we know, is the formula. NP.
In fact,
Sorry. What is the set? Now, what is the formula? NPR by n minus r factorial. Oh, that is not r factorial. Sorry, that's a mistake. Not n factorial. N factorial by n minus r factorial, right?
Yes, sir.
No, that is a mistake.
Yes,
I
sir.
think. Sorry, I forgot the definition of that. So that is going to be equal to what? 5 factorial by 3 factorial. 5 minus 2. 3 factorial is okay. 1, 2, 3, and 5, 4. Okay, that's correct. So this is how we found the permutation number of permutations. For finding the number of permutations, we cannot use simply permutations, because if we use permutations, that will actually give all possible permutations of two elements taken from the set of all 5 elements. But if we want to get the number of such permutations, we need to use the list command. But in the case of binomial coefficients, this is not actually necessary, and we can directly use binomial command itself here. And what I think is we have almost covered all the basics in number theory, and whatever things are appearing in the syllabus regarding number theory, we have completed, like permutations, combinations, GCD, LCM, prime factorization, prime counting function, that prime pi that we have already seen, nth prime function that also we have seen. And what was that nth prime function? I think p dot unrank n. And divisors of number we have already seen, counting divisors, modal arithmetic, all these things. So I think we have almost covered, not almost, we have covered all the topics in the syllabus appearing in the number theory portion in the Kerala University syllabus. If there is something you may ask, or otherwise we may continue with the next thing probably in the next session. Now it's a time for asking questions if there is some.